They're one of the most common things in our galaxy. They're the final fate for almost every star that will ever exist, and that includes our very own sun. But at the same time, they're one of the most extreme objects in the entire universe, a place where the laws of physics are just stretched to their absolute breaking point. We're talking about white dwarfs. So, when astronomers back in the early 20th century first pointed their telescopes at these things, the reality of what they were seeing was so bizarre, so nonsensical that this was their reaction. The great Arthur Eddington really nailed the scientific shock of the time. It was like the universe was telling them something that was flat out impossible.
So, how do we unpack this puzzle? How do we make sense of a star that top scientists first dismissed as just nonsense? Well, let's dive in and see what makes a white dwarf so incredibly strange.
Okay, here's the absolute heart of the paradox. I want you to try and picture this. Take our entire sun, all of its material, all of its crushing gravity, and squeeze it down into a ball no bigger than our planet Earth. That's a white dwarf. You've got the weight of a star in the space of a planet. The result is a density that's, well, it's almost impossible to wrap your head around. A white dwarf is, on average, 1,000,000 times denser than our sun. A single sugar cube's worth of this stuff would weigh a metric ton.
Let me put it another way. A piece of a white dwarf that weighs as much as a car, you could hold it in a matchbox. We are talking about a form of matter that is just completely alien to anything we have here on Earth. So, a huge question comes up. How does something so ridiculously extreme even get made? Well, they're not born this way. A white dwarf is what's left behind after a star like our sun dies. It's a stellar ghost. And this isn't some rare, bizarre thing that only happens once in a blue moon. No, this is the standard retirement plan for over 97% of the stars in the Milky Way, which means, yep, in about 5 billion years, this is exactly what's going to happen to our sun.
So here's how it happens. It all starts when a star runs out of its main fuel, hydrogen. It then swells up into a huge red giant. After that phase, the star basically puffs its outer layers away into space, creating these absolutely beautiful clouds we call planetary nebulas. And what's left in the middle, exposed for all to see, is that searingly hot, unbelievably dense core, the brand new white dwarf.
Now, this brings up a massive problem. Normally, a star has nuclear fusion pushing out against gravity, but in a white dwarf, that's gone. So gravity is trying to crush it into nothing. What on earth is holding it up?
The answer is something that sounds like it's straight out of science fiction: electron degeneracy pressure. It's this bizarre quantum effect. The electrons are just packed in so tightly, they can't physically get any closer. They basically form a quantum firewall that pushes back against gravity with incredible force, holding the entire star up without any fusion at all. And this table really just drives the point home. I mean, look at water, then osmium, the densest thing you can find on our planet. Even the core of the sun, it doesn't come close. A white dwarf is just in a totally different league. The numbers are staggering. And because of that quantum pressure, you get this really strange rule that just seems backwards. With a normal star, if you add more mass, it gets bigger, right? Makes sense. With a white dwarf, it's a total opposite. The more massive it is, the smaller it gets, because that extra gravity just squeezes it down even more. But even that quantum firewall has a breaking point. There is an absolute final limit to how much mass it can handle before it fails. This critical point of no return is called the Chandrasekhar limit, named after the physicist who first figured it all out. And that limit is a very precise number, 1.44 times the mass of our sun. If you can push a white dwarf past that line, the quantum support system breaks, gravity wins instantly, and you get one of the biggest explosions in the entire universe. So what happens to a white dwarf really depends on its life situation. Is it all alone out there in the dark, or does it happen to have a neighbor, a companion star? You see, its life can go down two totally different roads. If it's by itself, it just has a long, quiet end ahead. It'll just cool off over trillions of years until it becomes a cold, dead cinder called a black dwarf. But if it's got a companion star nearby, it can start stealing material from it. And if it steals too much and crosses that critical mass limit, boom, it goes off like a bomb, an explosion we call a Type 1a supernova. Now, let's look at that quiet path for a second.
The cooling process is incredibly, and I mean incredibly slow. It starts off super hot, but after billions of years, it's only cooled off a little bit. The oldest ones we can even find are still glowing at about 4,000 Kelvin. It's going to take trillions of years, way, way longer than the universe has even existed, for one to finally fade to black. So our sun is headed for that quiet retirement. But don't think for a second that these stellar ghosts are just boring leftovers. They are actually incredibly useful clues that help us figure out the past, the present, and the future of the entire cosmos. Because we know exactly how fast they cool, they work like perfect cosmic clocks, letting us calculate the age of star clusters and even our whole galaxy. They're also planetary graveyards. As debris from their long-dead planets falls onto them, we can actually analyze their light to see what those planets were made of. And, get this, deep in their cores, the insane pressure eventually forces the carbon and oxygen to crystallize, basically turning the heart of an old white dwarf into an Earth-sized diamond. So these are the quiet, glittering embers of stars that were once mighty, holding the entire history of their solar systems locked inside. And as we get better and better at reading their light, you just have to wonder, what other incredible secrets are these stellar ghosts still waiting to tell us?